This next method is called the rectangular method, and it's one that's become popular on social media recently, and it is very similar to an array or lattice, but it's not quite as messy as lattice, and it doesn't visually take into account the size of the boxes for, like we did the arrays with the base 10 blocks. So this is another way to think about partial products. We're basically doing partial products in a rectangle. So we're going to do 300 plus 70 plus 2 for my top row, and 20 plus 5 for my bottom row. So because I'm doing a 3-digit by 2-digit, my box, my rectangle, is 3 by 2. So my first place is, and you can really start anywhere, but I'm going to start here in the 300 times 200, which is 6,000. And then I have 20 times 70, which is 1,400. I have 20 times 2, which will be 40. And then I have my 5s. My 5 times 300 is 1,500. 5 times 70 is 350. And 5 times 2 is 10. So if I add all these together, I'm going to do my top row first. 6,000 plus 1,400 plus 40 is 7,440. And 1,500 plus 350 plus 10 is 1,850. So I have 9,290 for my rectangle method. So again, it's just one more way to organize your partial products in a rectangle. And it's still kind of honoring place value a little bit more than the lattice method. I'm going to do one more rectangle method using numbers that have zeros in the place value to show you how you can make adjustments in your rectangle for those zero place values. So for this problem, we have 306 times 250, and I know that on the top we have 300. We don't have any 10s, but we have 6 ones. So I'm going to have 2 columns, and on my second multiplier I have 250. So I have 200 and I have 50, but I don't have any ones. So I have 2 by 2. My first place to start is 200 times 300, and that gives me 60,000. And I have 200 times 6, which is 1,200. 50 times 30 would be 15,000. And 50 times 6 is 300. So we're dealing with a lot of large numbers here, and sometimes when we have that traditional algorithm, 306 times 250, kids can get lost in all of those zeros because you've got to start with zeros down here, and it just gets really cumbersome for students sometimes with that traditional algorithm. So using an array or more of a partial products type model would actually give you a more accurate and less error in your problem. So now we're going to add those 4 different partial products. So 60,000 plus 15,000 plus 1,200 plus 300 will be, here, I'll just write them out here, 15,000, 1,200, and 300. So I have 76,500. Now, 3-digit by 3-digit multiplication really is not focused on much in elementary school. They do 3-digit by 2-digit, and then some 3-digit by 3-digit. But once you understand the algorithm or any of these other strategies, it's easy to apply it to larger numbers in whichever way you feel comfortable with. So this would not be a typical problem you would see in school, but it is something that might come up. And students have another way to tackle this problem. One of the last methods that we talked about, and probably an early one that you would want to show your students, is the array model. And you can start showing this as early as 3rd grade when you start just learning your basic math facts, and make sure that students understand that multiplication is this 2-dimensional array. So even something like, for students having the understanding that 7 times 2 is the same as an array, that is 2 by 7. And that's a really important concept for students in 3rd grade to have. So the problem that we're going to work first is 24 times 7. And I have it modeled here as an array because I have 10 plus 10 plus 4, which is my 24. And I have 7 down the side. So when I think about this array, I basically have 2 different parts to it. I have the 7 times the 20, which is this green block. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 tenths. So 140. When you're first talking about the array, you can even break it down into all of its partial products. So we could do 7 times 10 is 70, and 7 times 10 is 70, which gives us 140, or 14 tenths. And the second part that we have is the 7 times 4. And it's my yellow ones. So I have 7 times 4, which is 28 ones. I don't know what happened to my 0. So if I want to come over here and record that, because we want to move students into a method of recording their work, their thinking, that is clear and understandable and efficient. So I have 24 times 7 over here. And the first thing we did was the 7 times the 2, or the 7 times the 20. So 7 times 20 is 140. And I only have a tens and a ones column, so I'm going to go ahead and put a hundreds column, because we do have over 10 tens. In this case, we have 14 tens, or 140. So 7 times 2 is 140. And then I want to do the 7 times 4, which we said was, my 8 disappeared too, was 28. And I can add those 2 arrays together. I'm going to add the 140 plus the 28, and I end up with 168 for 27 times 4. And I know this looks like a lot of writing and a lot of mess on the page, but remember, these are just the steps to get to the most efficient model, the most efficient algorithm for the student. and these are building blocks. So when parents start to question why the method is so long and cumbersome, it's because we're building up to the most efficient model, but we're making sure we have all those baby steps along the way. The next array that I'm going to model is 23 times 15. So I've got my array built already, but let me just refresh our memories on what the array models actually. So this top row is 20 plus 3 for 23. And we know this is 20 because along the top here I have 1 10 and 2 10s, and then 3 1s. Okay? And on the side I have 10 plus 5. And again, I know that because I know I have a 10 here and 5 1s going down the side. So that's where my 20 and 5 comes, 23 and 15 comes from. So now we can do the multiplication and my partial products. And my first one I'm going to do is 20 times 10. In my written record, I have 20 times 10, and I can see that 20 times 10 is 200. When I modeled it with the base 10 blocks. And I also just know that 20 times 10 is 200. So using my columns to organize my numbers, I have 200. The next one that I'm going to do is 5 times 20. So that's right here, 5 times 20 in my written record. And I can count that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tens, which is 100. And I can go in here in my columns and write 100. And the next number that I might do is 10 times 3. I'm going to use green for that also. So I'm going to do 10 times 3. So here's my 10, and here's my 3 in my written record. And I can easily see that I have 3 10s, or 30. And last but not least, I have my last partial product, which is 5 times 3, with all my little ones down here. So I know that a 5 times 3 array is 15 ones. I add that to my running record, and then I can just add up all the 4 partial sums, and I have 5, 4, 3, 345. So the next array that I'm going to do is 52 times 23, and I'm not going to use the base 10 blocks this time. I'm just going to model it with a rectangular array. So it's going to be a lot like that rectangle method we did earlier, but I'm going to try to keep it kind of proportional. So on my top here, I'm going to have 50 plus 2. And down the side, I'm going to have 20 plus 3. So then I can build out my rectangle. So I have 4 partial products that I'm going to work with, and I'm going to use my algorithm, or use my written record, to start to develop my written algorithm as I use the array, just like we did in class. So first, I'm going to start with the 20 times 5, or 50, and 20 times 2. So 20 times 5, 20 times 50 is 1,000. And 20 times 2 is 40. So for my 2 and the 23, for my 20, I have 1,040. I'm going to go ahead and draw a dividing line for my thousands just so I can keep everything straight. And then I'm going to work with the 3. in the 23. And I'm going to do 3 times 50, which is 150, and 3 times 2, which is 6. And if I want to write that down on my written record, I have 3 times 52. 3 times 52 is the 150 plus the 6, so 156. That gives me 1,196. One more array, and then I will end the arrays and just move on to just the straightforward written record algorithm. And this time we're going to do 75 times 36. So again, I'm going to build my array, and I'm going to try to keep it fairly proportional. So I'm going to have my 70 and my 5, 70 plus 5, and then I'm going to do 30 plus 6, and then I can build out my array. So I have my 4 partial areas, my 4 partial sums, and I'm going to start with the 30, and I'm going to do 30 times 70, which is 30 times 70, which is 210. No, 2,100, sorry. And I'm going to do 30 times 5, which is going to be 150. So I want to put that on my written record. I'm going to do it all at once. 30 times 75 is the 2,100 plus 150. So I have 2,250. And then I'm going to do my 6 and my 36. So 6 times 70 is 420. And 6 times 5 is 30. So my written record, I have 6 times 75 is 420 plus 30, so 450. So altogether, I have 2,700. And the last thing that we're going to do is just kind of bring it all together and talk through the more traditional algorithm using the base 10 language. That is so important, and kind of keeping in mind what we're multiplying. And I know that traditionally we multiply from right to left, but I'm going to show you how you can do it from left to right as well. It really doesn't matter which number you start with, because you're just going to add them up. And as long as you use base 10 language, it'll be clear what's going on. So let's start with 373 times 12. And I'm going to start by multiplying the 10 and 12 by 373. So we have 10 times 3, which is 30. And I know to put the 3 in the tens column because it's 30, not 3. And then I have 10 times 7, or 10 times 70, which is 700. So I have my 7 in the hundreds column. And I know that 700 plus 30 would be 730. And then I'm going to do 10 times 300, which is 3,000. So 10 times 370 is 3,730. And then next I'm going to do the 2. And I do 2 times 3 is 6. 2 times 70 is 140. So I'm going to put the 40 down. The last thing I wanted to show you is an algebra connection, and it's really important for you as an elementary teacher to know where your students are going in future grades, and even as high as in algebra, because what you're doing now in elementary school is really laying the foundation for so much of their math understanding. And one strong connection is when we're doing algebra and polynomials and things like x plus 3 times x plus 2. And you probably remember, or have tried to forget, that we do the FOIL on that, where you would do the first, the outside, inside, and then the last. And we are actually going to model that with an array so that we can see where those numbers actually come from. And to do that, we have these algebra tiles, and they come in kits just like the base 10 blocks, only they have 3 specific shapes and sizes. And we have usually a large square, which stands for x squared. We have red rectangles, which stand for x. And then there's individual small pieces, which are units. So we can build our array using these algebra tiles. The first thing that we would do is model x plus 3 across the top of our array. And then we would model x plus 2 down the side. So when I do that, I'm going to first start with x times x, which is x squared. And then we're going to multiply x times 3, which will give us 3 x's, and we model those with the red rectangle. So there's 1x, 2x, and 3x. And then we would do 2 times x, which again is just 2 x's. So I have this one over here, move it over. And one more x gives me 2x. And then finally we're going to do 2 times 3, which is 6. So I'm just going to do a rectangle, but I'm going to break it up into 6 ones for us. So you can see from our problem that we have x squared, which was our first. Then we have the outside, which is x times 2. So we have 2x down here. The inside, which is the 3 and the x. 3x. And then the last, which is 2 times 3 plus 6. So we can see that we have x squared plus 5x plus 6, and it's a really cool connection to the array. And when I was able to use that with my algebra students, they hands down understood foiling and factoring much easier. So it was a great algebra connection to what they had learned in elementary school.